So this is going to be a solid, so you don't have to worry about that. So basically what we're going to do is we're going to let the concentration of the magnesium ions be X. Okay? I don't know what it is. I'm just going to let it be X. But what would the concentration of my hydroxide ions be? Nope. It'd be 2X, right? Okay? So this is going to start at 0, and then some of this is going to ionize. I don't know what it is, but it's going to become X and it's going to become 2X, right? So at equilibrium, my magnesium ion concentration is X, my hydroxide ion concentration is 2X. So now what I can do is I can sit here and go, okay, I know my magnesium ion concentration times my hydroxide ion concentration squared has to equal 1.8 times 10 to the negative 11. Now, this is where you have to do a little bit of algebra, okay? Not a whole lot. When I take 2X and I square it, I get
4x squared.
4X squared. 4X squared times X gives me
4x cubed.
4X cubed. Okay? So if I don't know what these concentrations are, this is like a non-buffered solution. Oh, it goes into X and 2X. Now here's what's different. You all are used to acids ionizing in a 1-to-1 ratio because it's hydronium ions and the anions. With this, because of cations and have to balance out the charge, this might be 2X. Rarely you might get 3X. Okay, so if it was like a 1-to-3 ratio, then you'd have 3X cubed, and then you'd get like 27X to the 4th. Okay, that's pretty rare. Most of the time it's in a 1-to-1 ratio or a 2-to-1 ratio like this. So how can I get what X is going to equal?
Divide by 4.
Divide by 4 and then take the cube root. So somebody divide by 4 and take the cube root of that.
1.65 times 10 to the negative 4th.
Okay? Now, that's the concentration of my magnesium ions. What would the concentration of my hydroxide ions be?
2 times 3.
Yeah, so
3.
that's my magnesium ion concentration. So 2X is going to give me my hydroxide ion concentration. So Bruce, take that times 2.
3.30
times 10 to the negative.
Okay. So when Mother Nature's at equilibrium, this is the concentration of my magnesium ions. This is the concentration of my hydroxide ions. And life is good. Okay? Mother Nature is cool. She's chilled out at this point. Okay? This is what she wants. But when I mix these highly concentrated values, okay, of 0.5 and 0.5, Mother Nature goes, whoa, boys and girls, I can't handle this. Okay? This is way, 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 way too concentrated. Okay? Way too concentrated. So I'm going to make some of you form precipitates until I can get to the point where my magnesium ion concentration is 1.65 times 10 to the negative 4th, and my hydroxide ion concentration is 3.2 times 10 to the negative 4th. Okay? So once she gets to that, then she's chilled out. So what happens is that even though I added a whole bunch of water, okay, you'll notice that I've still got this layer of precipitate down here at the bottom. So even though I added a whole bunch of water, here's what's important. The concentrations of these ions up there are still the same, okay? Because that's when Mother Nature is most stable. That's the bottom of this energy well, okay? So now, if I added enough water, what would happen is that the concentrations would drop to these points exactly, and then you wouldn't see a precipitate because the solution would just exactly be in equilibrium if I added enough water. So in other words, it would dissolve until this happens. Now, if I kept adding more and more and more water, eventually the solution would become more dilute than this, and then you have no chance of seeing a precipitate. It'd be like I walk in and there's only 6 of you. Well, if my equilibrium is at 12 and there's only 6 of you, hey, I just won't make anybody sit down because I've got more room and I can hold more room. Okay, I can handle 6 more kids. So if you do your QSP and it's less than your KSP, that means that you're not going to make a precipitate because of the fact that your concentrations are less than what it takes to be in equilibrium. Yes, ma'am?
But the way would you find like the concentration of like magnesium or hydroxide is still the same through the KSP method?
Yes.
Okay.
Now, tomorrow we'll get into some variations on the thing. Because what can happen is like, what you could, like you might know like your hydroxide ion concentration, it would be like a buffered solution. So if I tell you like the pH is 7, okay, then you would know what this concentration is to begin with. And then you just have to solve for your magnesium ion concentration. But no matter what, and this is your overriding theme, no matter what, Mother Nature wants a concentration where you're going to get 1.8 times 10 to the negative 11. Okay? Good with that?
Wait, 1.8 times 10 to the negative 11 for all? No.
No, just
Just
for
for
magnesium
magnesium.
hydroxide.
That's right, okay.
Yeah, I mean, they're all over the place.
That's what I was, yeah.
Yeah.
Just double checking.
Yeah. Okay? Now, that's the process if the concentrations or as if the volumes are the same. The volumes are the same, your concentration is just half. Now, if let's say that I had mixed 10 milliliters of a 1 molar solution of magnesium nitrate, and I had mixed only 5 milliliters of sodium hydroxide. Okay? The process is still the same. You find the number of millimoles. Oh, I got 10 millimoles of my magnesium nitrate, and I've got 5, and that's a 1 molar solution as well. So I've got 5 millimoles of my sodium hydroxide. But again, here's what's important. I have to have the concentrations after they are mixed, okay? Not separately. I need them after they've been put together. So what's the total volume? Oh, 15 milliliters, right? Okay? So I'm going to divide by the total volume. Y'all are familiar with this. You're going to do it tomorrow on the quiz when you have, oh, here's the volume, here's the millimoles of my anion. I need the concentration, okay, divided by the total volume. So 10 divided by 15 is like 0.667 molar. 5 divided by 15 is 0.333 molar. So now when I calculate my QSP, it's my magnesium ion concentration times my hydroxide ion concentration squared. So that's going to be 0.667 times 0.333 squared.
What do you have to do with hydroxide?
Huh?
Oh, that's the square.
Yeah. So yeah, because that's the sodium hydroxide. Okay? And whatever number you get, your QSP is still going to be much, much bigger than your KSP, and you're still going to form a precipitate. Now, here's, and this rarely happens, but I need to point this out just in case, okay? In this situation, your magnesium ion concentration is the same as the concentration of your magnesium nitrate. If you needed the concentration of your anion, like let's say for example you needed the concentration of your nitrates, what you would have to do, what you would plug in here is actually double that. Okay? So when you look at the individual compounds that are ionizing, if what you need is like if there was like a 2 in front of it and you get twice that amount, you have to take that into account when you're actually doing the concentrations here. So in this situation, the concentrations that I needed were in a 1-to-1 ratio with the compound. If they weren't in a 1-to-1 ratio, then these concentrations would be like twice. So like let's say you have, I don't know, sodium carbonate, okay? And that's going to ionize into 2 sodium ions and a carbonate anion. And so let's say this is 0.1 molar. So your concentration of your anion, of the sodium ions would be 0.2 and your carbonate would be 0.1. So if you needed the concentration of your sodium ions to plug into your QSP calculation, then that you'd have to double that up and get 0.2. Okay? Cool with this. So what you're going to do on your assignment is that the first thing you're going to do is you're going to figure out the net ionic equation. If you're not sure what your precipitate's going to be, look in your book on page 1093 And you're only going to have KSP values, guess what, of things that are insoluble. You'll never have KSP values of magnesium nitrate. You know why? Yeah. Now, here's the other thing. Okay? This is where you look at science in terms of trends. If you look down those KSP values, they're really, really small numbers. Okay? Like 10 to the negative 28th, 10 to the negative 53rd, okay? 10 to the negative 13th. Okay? They're really, really small values. Same thing if true of Ka values. Okay? All Ka values are really small numbers. Okay? For your weak acids. So we're not going to have Ka values of magnesium nitrate because they'd be really, really, really big numbers because magnesium nitrate is soluble. So just like you're not going to ask, hey, Burkamp, what's the Ka value of hydrochloric acid? Okay, and I just scowl at you. It's like, because it's basically undefined or really big. Same thing would be happening of KSP values of something that's soluble. Okay, so you're only going to find KSP values of things that are insoluble. Okay, so you're going to, today's assignment is relatively short. So literally, you're going to have one reaction where you have lead 2 nitrate and sodium hydroxide, and then the next one is going to be silver nitrate and sodium carbonate. Okay, that's it. So you're going to write the normal equation, and then you're going to write the net ionic equation. But again, so here's the deal. And don't get confused on this. When you write that net ionic equation like this, that is going to be the net ionic equation for the formation of the precipitate. But in terms of your calculation of KSP, remember this gets reversed because from the KSP perspective, you're talking about that magnesium hydroxide dissolving to reach that point of equilibrium. Okay? So, we're cool with this. Okay? That's the difference. All right? Okay, so let me hand this out. So, stop that for a second.